Thank you for inviting me. It is a great opportunity to introduce this small project just started. It is called IDOLEI, so an ontology dedicated to Leishmaniasis. Oh. Okay. But why me? Actually, I am an outsider. I am a medical doctor specialized in internal medicine with experience in the field of amyloidosis diseases. So why did I start this project? Because I was asked so by a group of people working on it, since I already formalized for rare diseases knowledge difficult to annotate because sparse through several resources. And they were also many, as you can see, about 30, so it was very difficult to integrate all of that. And rare and neglected diseases are actually more similar than expected. For example, more connected, better. This one is reactive amyloidosis, which means that it is a rare disease due to persistent chronic inflammation. And as you can see, patients with visceral leishmaniasis co-infected with HIV developed AA amyloidosis. So actually, many diseases, more than we can imagine, are really connected. So I will introduce briefly what ontologies are, the consortium working on building a broad range of infectious disease ontologies, and the domain extension for Leishmania. I don't know how many of you are acquainted with ontology definition, but if you recall something from philosophy, ontology in philosophy is the study of what exists and the relation among entities. In the biomedical field, we have to think that we have to represent what exists for the machine. So the knowledge representation is not for humans, but for the computer. There is a consortium called Open Biomedical Ontologies Foundry, which is an open source, and it is a family of interoperable, non-overlapping biomedical ontologies built around the gene ontology, which is the most popular and most developed among them all. It is since 2001 that it is going to be one of the most powerful resources for functional enrichment analysis. Gene ontology is about gene products functions. It is divided in 3 categories: cellular component, biological process, and molecular function. So entities in OBO Foundry are defined according to the same principles as in Go. Relation ontology is used as a common set of formally defined relations, and all the Foundry can be considered as a modular annotation catalog of English phrases, which is understood by the computer because it is written in a language, ontology web language or OBO, and it is open. So the process, it is built around some top-level ontology. OBO utilizes basic formal ontology as top level through the methodology of downward population. So having these about 34 classes or entities defining the ontology as top level to organize the knowledge in a consistent way, more than 100 ontology projects are currently using BFO. And this is an example. You can find the infectious disease ontology here as a domain level, and the geo-ontology divided for biological process, for molecular function, for cellular component. I will skip the philosophical definition of entities, but I will just take some time to explain the second top level, which is the ontology for general medical science. In OGMS, the process of each possible disease was defined and described according to shared principles. So the infectious disease ontology used BFO and OGMS as top levels, and then it tried to provide terms relevant to infectious disease generally, like infection, host, pathogen, vector, in order to not have duplicates, and to ensure interoperability between all the IDO extensions. Of course, the consistency of the terminology is depending on the principle used, which are guaranteed from the foundry. And it allows a parallel development by domain experts. In fact, there are already several infectious disease ontologies extensions already developed for malaria, for example, for dengue, for HIV, for influenza, and so on. And of course, they could be all together and singularly be applied for computational applications. This is a very brief introduction of the core, which is used as hub, whereas the domain ontologies are considered as spokes for the extension strategy. Lindsay Cowell at the University of Texas Southwestern is the coordinator of the project, and she's supervising also our domain extension. This is a very brief example of how the IDO core works in terms of OGMS. So a disorder in OGMS is, of course, an infectious disorder in IDO core. And the arrows report the relations between the terms. This is one of the last developed for dengue fever. And you can see, in order to avoid redundancy, the Myriot methodology was used, which is consisting in inheriting each term from previous ontologies already done, if the definition is not changed, so that at the end, the malaria ontology, gene ontology, the taxon from NCBI, vaccine ontology, influenza ontology, for example, and human phenotype ontology were all integrated in IDODEN, but IDODEN itself has already more than 3,000 terms, which are not redundant. We don't have to write everything, fortunately, in all RDF and XML schema, because there is an editor, Protégé, which is widely used and developed at the Stanford University. So, which are the primary objectives of IDOLEI? We want, of course, to represent the entities in the Leishmaniasis domain in a consistent way, using the IDO core. So, we want to foster interoperability with other extensions and modularity. And we want also to foster biomedical data integration and reuse on large scale. So applications could be annotations of data for any purpose. It could be a decision support system for diagnosis, or it could be a learning tool, it could be modeling. For example, we could model the effect of temperature for the vectors influence on the disease outbreak, and we could use it for drug discovery or repurposing, vaccine development. There is no limit in what an ontology can do. The developer decides what an ontology will do. And this is an example of from the top level to the initial low level of granularity terms for treatment. So we start with a BFO term, of course, which is the top level. Then we arrive at OGMS treatment, which has a definition. Then we have the domain Leishmaniasis treatment. We have the WHO recommended treatment, the treatment for visceral Leishmaniasis, And for example, we could have as a subclass, one of many, the treatment for visceral leishmaniasis caused by Leishmania donovani. So we don't only have a hierarchy in the ontology, we have also relations, for example, between Leishmaniasis and Leishmania donovani. I will not go deeper into the description of the rationale for it. And we also have many annotations related to each entity. For example, in this case, I wanted to show that any treatment, it could be, this term could be substituted with miltefosine, for example, as a grade of evidence, of course, in some context. So we are not showing here geographical location and so on. So the grade of evidence as a general definition and a particular definition, because WHO provides all of that, and there is no limit to the annotations that you can enter in an ontology. Another example is that a drug compound can have a drug target compound already known or a predicted target compounds. For example, we can find this information in Campbell, and we can annotate the Campbell ID in our ontology. And some of the gene products of Leishmania donovani can be drug target compounds or predicted drug target compounds in other resources like Campbell. So this is the power of annotations. How could we apply it? We don't need to include in an ontology a database. We need to link an ontology to any database. So in this very, very simplified example, we can imagine that IDOLEI, IDODEN, and whatever other ontology, you had an idea of how many can be in the IDODEN slide, could be annotated with terms in GO, so gene products functions, cellular components, biological processes, whatever, with KEGG pathways, and also with any term in IntroDB, which we found a beautiful application with a lot of possibilities for structure-based drug design. What we would like to potentially add, building a domain ontology, is to foster a functional enrichment analysis of genes, for example, trying to clarify what is not known at the moment. For example, GSK found 200 compounds for each of the kinetoboxes, but how to select more at the lower level of granularity, how to decrease the number of compounds and to be more selective, we don't know. Or for example, for the replicin, sorry for the replicin, thank you. I was thinking, we don't know, you said we don't know what these peptides do. So are they homologs with some other peptides? Maybe GO has annotated those sequences, we don't know. So there are so many possible applications, so it is upon the users to decide what they have to do and what they need to do. Thank you.